Hello. In this video, we're going to learn the basics of path analysis and its application to models when using twin data. And so by the end of this session, you should be able to identify the advantages of applying path tracing rules and using them in structural equation modeling, and to be able to apply basic path tracing rules to derive expected parameters that will come from these structural equation models. By way of background, we're going to talk about where we've been and where we're going. Up until this point, we have been more concerned with the left-hand side of our slide, which is talking about data preparation processes to derive observed variances and covariances of data. However, we are going to start moving towards the right-hand side of our slide, where we will focus on modeling the hypothesized sources of variation based on biometrical genetic theory and specific models that estimate genetic and environmental contributions to determine how this model is expressed using both equation form and path diagrams to derive the predicted variances and covariances coming from that model. The estimates of the predicted variances and covariances of the model is actually conducted through structural equation models. Path diagrams are visual representations of how we think about sources of variation, such as genetic and environmental influences, and how they contribute to a phenotype of interest, as well as how these contributions are based on the foundation that is established by biometrical genetic theory. Those visual representations are then statistically implemented in structural equation models using the rules of path analysis. So in the rest of this video, we're going to learn and practice applications of the rules of path analysis so they can be used to derive the expected variance and covariance matrices of models using twin data. Path analysis was developed around 1918 by Sewall Wright, who developed a logical model of certain relationships within and between generations of guinea pigs, and then drew a diagram representing these relationships to study weight at birth and weight at weaning. He could then determine the effects of causal paths, the signs of the paths, the distance of the variables in the model, and if certain variables were indirectly associated to a common cause, like heredity. Therefore, the use of path analysis has some advantages. First, it combines our knowledge on causal relationships with the degree of observed correlations. Second, the mathematical equivalence between relationships identified via path analysis can be implemented in structural equation modeling because they have a one-to-one equivalence that can be implemented via matrix algebra expression. Therefore, structural equation modeling is a unified platform for path analysis, regression, factor, and variance components models. Before we begin with path analysis models, we need to learn the basic features and rules. Here, we'll go over the basic features that you will see in any path diagram. The square boxes represent observed or measured variables. These are sometimes referred to as manifest variables because they are clear to the analyst since they have been measured directly. Circles represent unobserved or latent variables. Latent variables are not directly measured and represent variables that are difficult or impossible to measure. Triangles represent a variable that reflects intercepts or means. And the relationship among variables can be described using two types of arrows. A straight single-headed arrow represents a causal relationship from one variable to another, and a curved two-headed arrow represents a covariance or correlational path. As we build on the path diagram conventions, we now turn to the rules that guide how to use these conventions. It is important to remember the foundational rule of path analysis, which is the correlation or covariance between any two variables can be expressed as the sum of the compound paths connecting them. So what does that look like in practice? First, let's define the term compound paths. When we are referring to compound paths, we are talking about all of the paths that connect two variables together to estimate their covariance. When estimating the effects due to a compound path, there are a few specific rules to remember. The first rule is that in order to begin identifying the compound path between two variables, you start with a variable and follow single-headed arrows in a backwards direction. The second rule is that you will be faced with paths that contain double-headed arrows. These double-headed arrows will allow you to change directions in your path progression. However, you can only have one and only one double-headed arrow in a single compound path. After you change directions, you can then proceed in a forward direction along single-headed arrows. You cannot go forwards and then backwards between two single-headed arrows. You can only change directions using double-headed arrows. After you have identified all the compound paths that contribute to a covariance between two variables, you will calculate the covariance in two steps. First, once you identify all the paths within a single compound path, multiply the path coefficients for that compound path to estimate the path estimate for that compound path. Second, sum up the path coefficients that were derived from each of the compound paths. Oh, one last thing. The covariance of a variable with itself is also referred to as the variance. It is possible to have distinct compound paths for the estimation of the variance if they have different paths or occur in a different order. So let's say you have a situation like this one, where we're going to have a single compound path and we're trying to estimate the covariance between variable A and variable E. The way we would estimate this path would be in the following manner. We would travel backwards along path A. Then we would multiply the path estimate from path B. We would go around path C, and we would multiply that with the estimate of path D, as well as the estimate of path E. So the path estimate from this compound path would look like A times B times C times D times E. Now let's say you have a situation, let's say we want to estimate the covariance between A and D. If you said that the path estimate is A times B times C, you would be right. Now, what if we have a situation like the one we have identified here, where we are estimating the covariance from A to C? Then we would estimate the path in the following way: A times B times C. But what if we have a situation like this, where we're trying to estimate the variance of C? If you said the answer is C, you would be on point. If we want to estimate the variance of A, but also taking into account the covariance that A has with B and C, you would estimate that path as A times B times C, and then we're going to come back down to B times A. So A times B times C times B times A. Now we have another opportunity to strengthen your skill through this example that has multiple compound paths. Here, we want to estimate the variance of C, taking into account that we have two latent variables, F1 and F2. So we need to think about all the compound paths that would contribute to the variance of C. So how many ways can you get from C back to C? One way could be back through A, around to E, and back down through A. To that, we could add on another path from D to F, back around to D. But there's still another way. You could go from A around to C and back down through D. And yet there's still another way because we can go through the opposite direction. So we can go from D back around to C and back down through A. And as you can see, once we have identified all these compound paths, we add up their estimates to come up with the variance for C. We're going to take a little bit more practice, and we're going to calculate the covariance between C and D. So how would we go about doing this? If you said C times VD, you would be right. But there is another way to go. You could go D times E. Now, what you cannot do is go around D and then to VE and then to E. Why? Because you cannot have two double-headed arrows in a path. So let's try our skill some more and calculate the covariance between B and C. If you said A times VA times B, you would be absolutely right. One thing you need to keep in mind is that you cannot say C times D. Why? First of all, you cannot use C as your first path because you would be going in a forward direction. You need to begin your paths in a backwards direction. And so a C times D path would be incorrect. Additionally, you need to use a double-headed arrow to switch directions, and you don't have one here. Okay, so far we've been talking about practice variables, but let's take an example where we might actually see a path diagram representing something that we generally see in our analyses, which is linear regression. Here, I have an example of a measured variable called weight, and we're interested in estimating the relationship between site and weight. And so if we're interested in understanding the relationship between site and weight, we would also consider that weight has an intercept denoted by beta 0, and there's some source of error variance that's also contributing to weight. So if we were to articulate a linear regression as a path diagram, we might do so with the following figure, and we would say that beta 0 plus beta 1 times site plus the variance due to epsilon would be equal to weight. Now we've talked about path analysis, the rules, and also a simple explanation of how we would apply it to a regression model. But we can also use this path analysis approach to study twin data. And over the course of the next several sessions in the workshop, you're going to see more and more path diagrams. So in order to get you comfortable with the idea of working with these types of path models, we're going to do some practice and see how they come about and how we work with them. So what are we looking at here? Here we have a variable called weight that has been measured in two members of a twin pair, as denoted by the squares. Weight also has a mean, as denoted by the triangle, and arrows leading to weight. We have latent variables that represent the variance due to additive genetic effects, A1 and A2, common environmental effects, C1 and C2, as well as unique environmental effects, E1 and E2, as denoted by the circles. These latent variables influence weight, as denoted by the single-headed arrows from the circles to weight in the squares. It is also important to note that latent variables A1, C1, and E1 have variances of VA, VC, and VE, and those cause phenotype weight via the path coefficients of 1. This is the same for both twin members. Additionally, the covariance between A1 and A2 is denoted by VA for MZ twin pairs and 0.5 VA for DZ twin pairs. This accounts for the fact that MZ twin pairs share 100% of their genetic effects, and DZ pairs share, on average, 50% of their genes. So you see that I've now taken apart the figure a bit, and I'm now focusing on each individual member, twin 1 and twin 2. So how would we calculate the variance of weight for twin 1? We would do so in the following way. We would use our path tracing rules to estimate all of the sources of variance on weight. And so in the first instance, we would take the path 1 times VA times 1. We would do the same for VC. So we would then have a path due to VC as 1 times VC times 1. And to both of those paths, we would add the variance due to E, which would be 1 times VE times 1. And so to calculate the total variance of weight for twin 1, we would estimate that as a VA plus VC plus VE. We would do the same thing for twin 2. But what about their covariances? How do we estimate those? Again, we're going to use those path diagram rules and apply them to this situation. Here, we're going to focus on MZ pairs, and we're going to first identify the path of genetic variance, which is 1 times VA times 1. And to that, we're going to add the path that's due to shared environmental influences or common environmental influences, which is 1 times VC times 1. And then we're going to add those paths, and we would estimate those as VA plus VC. Now, how would we represent the covariance of weight between members of DZ pairs? We'll use the same rules, and now we're going to estimate the variance due to genetic effects as 1 times 0.5 VA times 1, or 0.5 VA, plus 1 times VC times 1, or VC, and we add those two up to estimate the covariance for DZ pairs. So if we were then to put all of these estimates of variances and covariances together in a predicted matrix, your matrix would look something like this, where we would have the variance of twin 1 against the variance of twin 1, estimated as VA plus VC plus VE. And we would estimate the covariance of twin 1 against twin 2 as VA plus VC. Similarly, for the variance of twin 2 against itself, we would have VA plus VC plus VE. And similarly, when we put everything together for DZ twins, your variance and covariance matrix would look like the matrix that you have on the right-hand side. Okay, you can stop here and take a break if you'd like, or if you'd like to test your skills of basic path analysis, specifically using additional twin models, hang on. So we have two additional models that we're going to work on where you can test your skills. The first one is an ADE model. You have been introduced to the concept of dominance, so we'll not explain the concept of dominance here, but rather show you what an ADE model or a model that also includes dominance looks like using twin data, and allow you some time to derive the expected variance and covariance matrix for yourself. So if you want to pause me for a moment so that you can derive the same matrix variance and covariance matrix that you did for your ACE model, you can do so. So if this is what your expected variance and covariance matrix looks like for MZ twins, you'd be good to go. This matrix looks just about the same as your ACE model, where you're just replacing the VC with VD. So you have a VA plus VD plus VE. The same can be said for the covariance between twin 1 and twin 2 of an MZ twin pair. You're just replacing the VC with a VD. So you have VA plus VD. Where it gets juicy is how the variance and covariance looks for DZ twins. The variance stays the same, VA plus VD plus VE. But when you're looking at the covariance, you have to include your 0.5 VA, which is similar to your ACE model. And now you're adding to that 0.25 VD plus VE. One last opportunity to do another test of your path analysis skills, at least for twin models, is using this path model for a classical twin approach that you've seen in some of the older literature, where you now have your path estimates on the causal line and the variances to be fixed to 1. So given this representation of a twin model, what do you think your expected variance and covariances matrices look like? Again, if you'd like to pause me, you can do so while you put it together. If you said that your expected variance and covariance matrix from this twin model looks something like this, you would rewrite. Because remember, you're going to estimate the path A, go around the variance of 1, and then come back down the path A. So that would give you A squared. And then you would add to that your C squared, and add to that your E squared. And then you would estimate the covariance of your MZ twins as A squared plus C squared. So the same would be done for your DZ twins, except for now your covariance would just be 0.5 A squared plus, as we discussed here, the goal of path analysis is to work out the predicted variances and covariances of variables given a specific model. In this case, we focused exclusively on a univariate twin model and specifically an ACE model. We did some extra practice with an ADE model to prepare you for future situations. But as you go through the rest of the sessions, the path diagrams will become more complicated. So with that, I thank you for your time. I've got some references here related to the Sewell Wright readings. And if you have any questions, please reach out. Thank you.